So let's actually make the connection between vectors and matrices. So let me start off with this question. There's some similar questions in your homework. So we've got U, we've got V like we had in the previous video. And the question is just, is there some combination of U and V that will give you 214, the vector 214? And by combination, we mean the same thing we meant before. So like a combination of U and V would be something like 2U plus 3V, which we saw in the previous video does not make 214. It makes something else, right? It's like 2 times 2, 3 plus 3 times negative 3, 1. So that's 4, 6 plus negative 9, 3. And that makes negative 5, 9, right? So that's one attempt to combine U and V, but it does not combine to make 214. So there must be some way though, or maybe not, but let's find out. So really what we're looking for is we don't know the weights of each vector. We don't know the 2 and the 3. So what we have is an x, x1, times 2, 3, and an x2 times negative 3, 1. And we want that to come out to 14. This is a vector equation. Say, can you combine a couple of vectors to get a different vector as a result? But let's go ahead and actually simplify this the same way that we did over here. So let's do the multiplications first, the x1 and the x2, and then do the addition. So we'll get something like 2x1 and 3x1 as a vector. It's still a vector. It's still just got one entry on the top, one entry on the bottom. Not a matrix. And likewise here you get negative 3x2 and x2. So another vector, and we want that to result in a vector 214. And now we'll go ahead and do the addition. And these are not like terms, they have different variables, so we can't really combine them, but we can write this as a single vector with one algebraic expression in the top entry and a different algebraic expression in the bottom entry. And we still want that to come out to 214. And the only way that this vector is going to equal that vector is if the top equals 2 and the bottom equals 14. So that gives us two equations to solve. It gives us, I'll put it over here. It gives us 2x1 minus 3x2 has to equal 2, and 3x1 plus x2 plus x2 has to equal 14. And lo and behold, this vector equation really is a system of linear equations in disguise. And we have a method for solving systems of linear equations, row reduction. So all this new language of vectors and vector combinations, and we're coming back to our same old technique to actually solve of row reduction. So let's do that. Let's see, the corresponding matrix here is going to be 2, negative 3, 2, 3, 1, 14. And we just need to put that in row echelon form, maybe even reduced row echelon form to actually go ahead and solve this. Normally you'd start by putting a 0 right here where this slot is, and that really is still our first goal. I'm not particularly enamored of multiplying the top row by negative 3 halves and adding to the bottom row. That's fine, but I'm just not super fond of doing fractions by hand. So I'm actually going to start by just dividing the first row by 2. That's one of our legitimate row operations, or actually multiplying a row. So multiplying a row by 1/2. So multiplying the top row by 1/2. So that become 1, negative 3/2, 1. Bottom row 3, 1, 14. There's still a fraction, but I've put it off, at least for a step, put off dealing with it. So that was 1/2 of row 1 becomes the new row 1. And now I'm going to say negative 3 of row 1 added to row 2. So negative 3 of row 1 added to row 2 will become the new row 2. So top row still 1, negative 3/2, 1. Bottom row will become 0. And now is where I have to be a little bit careful with my fractions. Negative 3 times negative 3/2, negative times negative is a positive 9/2. So 9/2 added to 1. 9/2 added to 2/2 is 11/2. And negative 3 times 1 is negative 3 plus 14 is 11. Okay. Not too bad. This is already row echelon form. I've got that 0 in that one spot. And we could probably just figure out our x1 and x2 from here. But let's go ahead and keep going. It's not too bad to get this one into reduced row echelon form. So let's put a 1 where the 11/2 is. So that'll just multiply that second row by 2 11ths. So second row times 2 11ths. So 0, 1, 2 11ths. We'll cancel the 11, so just 2. That's kind of nice. And then to finish, we need to put a 0 where the negative 3/2 is. So we just need to do 3/2 of row 2 added to row 1. So 3/2 of row 2 plus row 1 becomes the new row 1. Squeeze it in there. Okay, and our final result here, 0, 1, 2, that's the row we're not changing, but we're doing 3/2 of this row added to that row, so that still becomes a 1. 3/2 times 1 is 3/2, added to 3/2 is 0. That was our goal right there. And 3/2 times 2 is just 3. Added to 1 is 4. So with a little bit of work, we were able to find out that x1 needs to be 4 and x2 needs to be 2. So apparently that's the right... Excuse me. Apparently the answer to this original question up here is yes, there is some combination of u and v that will make 214. And the particular combination that will do it is x1 needs to be 4, so it'll be 4 of 2, 3. And x2 needs to be 2, so plus 2 of negative 3, 1. That should make 214. I guess I'm kind of on the way to doing a check here. This is how you would check. And maybe I won't finish all the arithmetic. Let's just see if we can check that in our heads. That would be 8, 12 minus 6. So 8 minus 6 is 2. I like that. And 12 plus 2 is 14. Yeah, it works. So there is indeed some combination of u and v that will make 214. And I just wanted to point out that we have a combination, or sorry, a connection now between a vector equation and an augmented matrix. Notice that we just basically took the column vectors, including the one we want it to be equal to, slapped them together into an augmented matrix, and solve that to solve the vector equation. And this is true in general, and this is worth actually mentioning. So in general, solving a vector equation that has this sort of format of some combination of a first vector, some other amount of a second vector, a third vector, all adding up to make a fourth vector, a result, is the same as solving an augmented matrix, where you just make each one of those vectors a column of the augmented matrix. So again, not to beat a dead horse, but just as an example, if they wanted you to solve a vector equation that looked like x1 times 1, 2, 3, some combination of that vector, and some other amount of 4, -2, 7, and some amount of yet another vector, 7 to -4, and you wanted that to come out 10, 10, 10 for some reason. I don't know if that particular one can be solved. Actually, I do know. It can be solved. But the way that you would do it is to create an augmented matrix with those three vectors as columns and this vector as the final column of the augmented matrix. You would row reduce that and solve it. And since I probably just made it up off the top of my head, it's probably got horrible fractions as its solution, but it could be solved.